So at this point, we understand that two charges feel a force on each other at a distance. If I put a charge plus q here and a charge minus q here, they each exert a force on each other. And as we've discussed, the plus q, this one, exerts a force on the minus q, and I'll draw the force in, let's say, red. So the force on the minus q is in this direction. That's the electric force. The minus q exerts a force on the plus q, and that's in this direction. And those two forces are equal and opposite, and you know that the electric force is k q1 q2 over r squared, where r is the distance between them. So that's what we've been talking about so far. The magnitude of the force is kqq over r squared, and the direction is given by, we can write the electric force equation in terms of the radial direction, or you just know that two unlike charges attract and two like charges repel. So the important thing to understand for today's discussion is that these two charges feel a force at a distance. These two charges are separated in space, but they feel a force at a distance. So what is it that's being exchanged between the two? How does a charge exert a force on another charge when it's at a distance? If I want to exert a force on you, I have to walk up to you and push you or hit you. But I can't magically exert a force at a distance unless it's the force of gravity or the electric force. So the electric force and the force of gravity are these special kinds of forces that, unlike all the other kinds of forces we've talked about, think about it, all the other kinds of forces have to do with contact. The electric force and the gravitational force both exert a force at a distance that separates the two objects. So the fact that the plus charge, this one here, whoops, didn't mean to cross that one out, the plus charge, this one here, exerts a force on the minus charge, this one here, at a distance, means that there must be something that exists around that plus charge that extends outward from that plus charge, that exerts a force on the minus charge. How do we know that the plus charge exerts a force on the minus charge? Because we put the minus charge there and it feels a force. We know that that exerts a force on it. But what happens if I take the minus charge away? What happens if I take the minus charge away? Let's see if we can erase that. There we go. Getting there. Okay. Minus charge, go away. There it goes. Okay, so the minus charge is gone. Now there's a space there where the minus charge was. What is there that would exert the force on the minus charge? Is it gone now? The plus charge has some property that if I put a minus charge in that little red dotted circle, will exert a force on it. And that's the property that we call a field. So an electric charge exerts a force on another charge through what we call the electric field. There must be an electric field due to the plus charge at this position where the minus charge was. How do we know that there's an electric field there? We know that there's an electric field there because if we put a charge there, it feels a force. So there must be something there, and we call it the electric field. And what about over here? What if I put a charge there? Will it feel a force? Yes, of course it will. So there must be an electric field over there. Actually, if I put a charge anywhere in the vicinity of this purple charge, and it feels a force, then there must be a field there. So there must be an electric field everywhere in space around that plus charge. Now think about this concept of the electric field. It's that we say that if we put a charge down, this purple charge here, if we put that charge down, that it creates an electric field around it, such that if I put another charge somewhere, that other charge feels a force. And so there must be a field everywhere around this plus charge. Now, what is a field? Well, a field is a phenomenon that Sorry about that. The field is the phenomenon that a charge feels a force at a distance. So we say that even if we take away the charge that feels the force, that there must still be something there, and we say that there's an electric field there. So we can talk about the electric field of a charge. The same analogy holds for gravitational fields. Since there's a gravitational force between two masses, then if I take one mass away, a single mass must have a gravitational field around it, right? That's why we talk about the gravitational field of the Earth. The Earth has a gravitational field, right? So let's, how do I get another page? Hold on. So this is the Earth. That's kind of an oblongish Earth. But this is the Earth. Maybe we should make the Earth a more reasonable color, earthy kind of color. So here we go. Here's the Earth. And we know that if we put a massive object here, that object feels a gravitational force towards the Earth, gravitational force. And if I were to put a massive object there, it would feel a gravitational force towards the Earth. But there is no massive object there. Yet there must still be something there, and we call it the gravitational field. There's a gravitational field which points towards the Earth at any point around the Earth. So that tells us that if I put a mass at that point, that mass feels a force. So one of the important things to note is that how do we know that a field exists? Is there such a thing as a field measuring device? The only way that we can measure a field is to measure a force at a distance. So there is no physical way to measure a field. All we can do is actually measure forces. But we create this concept of the field as a thing that can exert a force at a distance must have around it a field. We can't actually picture that field. Well, we can picture it, but we can't actually measure that field other than measuring a force by putting another object there. That's the only way we can know a field is there. So how do we define this field? Let's go back to the electric charges. If I have a plus charge, plus Q, and let's just make it an object with a charge Q. That object with a charge Q, well, we know that if I were to put a plus charge here, right there, if I were to put another plus charge there, it would feel a force in this direction. If I were to put a plus charge, let's say here, it would feel a force in that direction. If I were to put a plus charge here, it would feel a force in that direction. So the field is just the force that it feels without the charge, and we actually define the field, the electric field, E is defined as the force divided by the charge. Not the charge that has the field, but the charge that would have felt the force. So if I were to put a charge Q here, or a charge Q here, or a charge Q here, I should probably differentiate these, that the field due to charge 1 is equal to the force on charge 2, divided by the charge 2. So think about this. If I'm talking about, let's go back to some more reasonable color. If I'm talking about the force on charge 2, that 1 on 2 is equal to k q1 q2 over r squared, then the field of 1 is equal to k q1 q2 over r squared divided by q2, and the electric field due to charge 1 is just k q1 over r squared. And the direction of the electric field, because electric field is a vector, the direction of the electric field is just the radial direction. Notice that the direction of the electric force is radially outward from charge Q1, so the direction of the electric field is also radially outward from charge Q1. Note, of course, that this is the electric field due to a point charge, and later on, what we're really going to get to is the electric field due to charge distributions. But the electric field due to a point charge is kq over r squared. It's radially outward from the point charge. That means that if the charge is negative, that the electric field is actually going to be radially inward, because it's going to be in the minus r hat direction. And then if we want to find the electric field of a distribution of charges, we just have to add up each of the individual electric fields. The electric field of a distribution of charges is going to be the electric field of charge 1 plus the electric field of charge 2 plus the electric field of charge 3 plus ... the electric field of all your charges. So note a couple properties about electric fields. Electric field is defined as the electric force divided by, or electric force per unit charge. Is the electric field, again, I'm going to repeat that. The electric field of any charge distribution is the electric force due to that charge distribution divided by the unit charge. Now what that really means is, imagine I have a collection of charges. A collection of charged objects. Let's say this is Q1, Q2, Q3, Q4, Q5. So far we've only dealt with 2 charged objects like the dipole, but you can have as many charged objects as you want. And we want to know what is the electric field of these charged objects. Well, we first of all have to ask, where do we want to know the electric field? If we want to know the electric field at some particular point, let's ask what is the electric field at this point right here. If I want to know what the electric field at that point is, what I have to do is I really need to put a point charge, Q, there, and ask what's the force on that Q due to Q1, Q2, Q3, Q4, and Q5, and then divide it by Q. So this little charge here, this Q here that I'm finding the force on and then dividing out, right? That's the charge Q that I'm dividing out. This is called the test charge. When we define electric field, we define the electric field as the force on a test charge divided by the charge of that test charge. So we'll note that each of these purple charges, Q1 exerts a force in that direction, Q2 exerts a force like that, Q3 exerts a force like that, Q4 exerts a force like that, Q5 exerts a force like that. Then we have to add up all those individual forces. Let's make that a red net force. The net force might be something like that. And then once we find that net force, we divide out the test charge to find the electric field due to the 5 charges. And then note that what we started with was, of course, that the electric field of a point charge is KQ over R squared R hat. But that's just the electric field of a point charge. If we want the electric field of a distribution of charges, we've got to add up, as we already said, E is equal to KQ1 over R1 squared, and then the R1 hat direction plus KQ2 over R2 squared, whatever direction that field would point in, plus KQ3 over R3 squared, plus whatever direction that's in, ... right? Just like I showed on the previous page, with the purple charges, all had different directions, all had different distances, all had different charges. So to find the field of a collection of charges gets complicated. It can be a difficult problem because we've got to add up all of these messy terms like vectors. Just keep in mind, because this is a common error, is that this right here, whoops, that didn't look too good, that this right here is simply the electric field of a point charge. If you want the electric field of anything more complicated, then you either have to add up, you have to break it up into point charges and add them all up, or if you, for some reason, already know the electric force, then in general, right, the electric field is equal to the electric force over the test charge. This is a general result. It is always correct. This is for only point charges. That's really important to recognize, because half of you at some point will use this for some general distribution, when really you just need to use this, or you need to use the point charges and add them up. So let's take, for example, the problem that we did in class yesterday, where we found the electric force that a dipole of the plus little q and the minus little q exerted on the big Q. I guess I should draw that. We found that the electric force of the dipole, whoops, wrong pen, let's try again. The electric force of the dipole, which was made up of a plus, a plus little q and a minus little q, and we asked if those two were separated by a distance d, and we wanted to know what the force was on a charge big Q at a distance r. We found by adding up the force from the little plus q and the force from the little minus q, and we found that the net force on the big Q was F net is equal to 2k q over the square root of d over 2 squared plus r squared times the cosine of the theta. I'm just trying to remember what we actually had done, where cosine theta was d over 2 over the square root of d over 2 quantity squared plus r squared. The point being here that we found the net force. The net force was in the x hat direction, if we call that the plus x direction. We found the net force on the charge big Q. So the question is what is the electric field of a dipole? So what is the electric field of the dipole at the position of plus big Q? Well, in this case, tricky, we've reversed our capitals and our little q's, and our test charge in this case is the big Q. So the electric field is simply the electric force divide out the charge that we're going to take away. What I want to know, and I'll draw it on a new page, is what is the electric field due to a dipole? Here's the plus q, there's the minus q, they're separated by a distance d at a distance r along that perpendicular bisector. At that point, what is the electric field here? The electric field there is the force that would be exerted on the charge there divided by the charge there. So the electric field is kq. Oops, now I have to remember what the rest of that term was. Kq over d over 2 squared plus r squared. There was a 2, and there's a cosine theta, understanding that we know what cosine theta is by doing some geometry. So that's the electric field at that point. What's the direction of the electric field? It's the direction of the electric force, x hat direction. So right now I don't want to get into the complexities of calculating electric fields by complicated charge distributions. We know that the electric field due to a point charge is the magnitude of the electric field due to a point charge is kq over r squared. Whoops, that's a squared. Kq over r squared, where r is the distance you are from the q. So if this is my q and I want to know what is the electric field at some distance r away, the electric field at that point is kq over r squared. It is radially outward. We know that. What I'm interested in talking about for the rest of this class is what is the direction of the electric field at any point. So let me just go to a new page and a new color. How about a yellow charge? If we have a yellow charge, oh, that is impossible to see. Well, I guess you can probably see that since you're watching a video instead of a projector, but let's make it a different color. Let's make it an ugly green. So we've got a charge plus q, and I want to know what's the direction of the electric field. What's the direction of the electric field right here, at this point that I made to the right? The direction of the electric field is the direction that the force would exert on a positive test charge. So if I put a plus charge there, it's going to feel a force in that direction. If I put a plus charge here, it's going to feel a force in that direction. If I put a plus charge here, it's going to feel a force in that direction, etc., etc., etc. So I can put plus charges everywhere, and I can draw as many or a few of these as I want. And so now what I've drawn is this is called an electric field map. The electric field map is really important for us to be able to visualize what the forces would be on charges that I put near my charge or my charge distribution of interest. And actually, these lines that I drew, they can extend all the way back to that plus charge, because no matter where I put a test charge outside of this plus charge, that test charge is going to feel a repulsive force away. And so what I've drawn here in this ugly green color is an electric field map. So notice a couple properties of this electric field map. The electric field map is an image that depicts the direction of the electric field on a positive test charge. Notice that also what happens if I could draw more and more lines. I could say, well, if there was one here.
So at this point, the video that I created for you screwed up, and it deleted something, and it deleted my audio for about 3 minutes. So now this might be a little awkward, but I'm just going to try to voice over what I had drawn. So what I took is the plus charge from that we were previously talking about, and just drew 2 times as many field lines, because no matter where I put a test charge, it's going to push it outwards. But the point that I was trying to make is that it doesn't really matter how many field lines you draw, because the field lines, the number of field lines don't actually mean anything. What is meaningful about field lines are the density of field lines, how far apart they are, and the direction of field lines. What's the direction of the force on a test charge at that point? So you can see in the image that I've drawn some purple dotted lines, sort of circles, in close to the charge. I'm showing that the field lines are pretty close to each other, and then out at the edges, the field lines are farther apart from each other. All that matters is that density of field lines. Where the field lines are farther apart, the force is smaller, or the field is smaller. Where the field lines are closer together, the force is larger. There's one here. I then show that because the field lines denote the direction of a positive test charge, that if I want to know what the electric field of a minus charge is, that the field lines must point inwards towards the minus charge. So on the top I show a positive charge and the field lines point outwards. On the bottom I show a minus charge and the field lines point inwards. Notice that still for the minus charge or the plus charge, when I get farther away, the force on the test charge is going to get smaller, so the field lines get farther apart. The direction of the field lines just tell you the direction that the test charge would move. So now I'm waiting for my text to come back again. And here it comes. So now I'm summarizing what an electric field map looks like. An electric field map has lines that originate, that start from plus charges and terminate or end on minus charges. And the density of the lines is equivalent to the size of the field. Notice that there's also a result of this, is that the electric field lines cannot cross. Think about it. If the electric field is the force per unit charge, and if 2 electric field lines cross, that means that at that point there would be 2 forces in 2 different directions. But the electric field is the net force per unit charge, and so you would, if you had 2 different forces, you would add them up and there would be a net force. So field lines cannot cross. So these are the general properties of an electric field. That the lines start on a plus and on a minus. Density of the lines is equal to the size of the field, or is equivalent to the size of the field, and that electric field lines cannot cross. And the electric field, of course, is defined by the net force divided by the unit charge. Remember that this equation at the bottom of the page is the general definition of electric field, and for the specific case of a point charge, the force between 2 point charges would be kqq over r squared, and if you divide out one of the q's and want to know what the field of one of the charges by itself is, that would be kq over r. But that's just the specific case of a point charge. In general, if I know the net force, the net electric force that some distribution of charges exerts on a test charge, then to find the field of that distribution of charge, I would divide it by the test charge.
the electric field of a dipole looks something like this. Again, recognizing that as these field lines, whoops, that was not a very good one, but notice that the field lines are more dense, close to the charge, less dense. Whoops, I probably should be doing that in a different color. Let's undo. More dense, close to the charge, less dense, farther from the charge. The field is larger in here. The field is smaller out here. The field lines originate from, they always point from a plus charge to a minus charge. So that's pretty much all you need to know about fields. Now what we'll do is we'll just start talking about fields and forces of charge distribution. So we're just going to add up the fields or forces due to point charge and talk about charge distributions. And that covers the next chapter. So here's your clicker question. I'm going to draw you a picture of 4 different fields, and I want you to tell me which of the patterns represent a possible electrostatic field. Any one of them, 2 of them, 3 of them, or all 4 of them may, but you need to tell me which one represents a possible field due to charges. So let's just isolate them. The boxes just mean that they're not going to. Actually, let me do that differently. Messing up things here. Whoa, something's going on. Okay, so let's just do 4 different fields. The four fields have nothing to do with each other. They're independent. Let me draw a field that looks like this. Whoops. A field that looks like this. Oops. Okay, I've drawn you the 4 fields. They're a little messy, but hopefully you can see these are 4 sets of potential field lines. And the question is which one of these, or 2 of these, or 3 of these, or 4 of these, show field lines that could be possible due to charges that are outside of the region shown. So there are no charges in the squares shown, but these are fields that are potentially drawn for charges outside of the region shown. Which ones of these are possible? I'll give you a couple seconds to think about that. Everybody has to vote. Everybody has to vote. Okay, so I'll just make this quick. The correct answer is, drum roll please. All right, whatever. B. The problem here, mostly it can be argued from the fact that electric fields must start on plus charges and finish on minus charges. And assuming that there are no charges in the picture shown, each of A, let me give a different color here, boop, I don't know how to, all right, let's just make it yellow. Each of A, D, and C have field lines that both start and terminate within the box. So these field lines don't even start and terminate on anything. They start and terminate on themselves. So a charge outside the box couldn't create these because these field lines do not start and terminate these, in part C. Part C. No, that's not C. Oh boy. That's D. A, B, C, D. D. Oh, that was really, really unpleasant. Okay. So this one was D. Okay, so the field lines in D don't start or terminate on anything except themselves. The field lines in C seem to come from nowhere. They start on these points that I've just drawn, but there are no charges in the picture, so that can't be correct. And the field lines in A terminate right here in the center and start right here in the center, but I said there were no charges in the box. So the only possible field is B. I'm not entirely sure how we'd make that field, but we can imagine some charge distribution where there's some positive charges on this side outside the box and negative charges on this side that are making these kinds of field lines. So B is the correct answer. Okay, one more clicker question. So I'm going to give you a dipole and put it in a field, and then ask which of these fields exerts a net force. Okay, let me ask that question again. Now that I've drawn a dipole, it's the purple box. It's got a minus and a plus charge in it, right? So that's just an atom that has some kind of separation of the minus and plus charge. It's a dipole, a minus and plus charge. And I put it in a field. A and B, the field varies as you go across the page. C and D, I guess I might have just given something away. In C and D, we've got a different kind of field, but the field is in green. And the dipole in B and D is at an angle, and the dipole in A and C is lined up along that central field line. The question is in which one of these situations, A, B, C, or D, is the net force on the dipole equal to 0? It could be more than one, A, B, C, or D, or A and B, A and C, A and D, etc. It could be more than one, but in which situation is the net force on the dipole equal to 0? I'll give you some time to think about that. Okay, rather than me putting in 2 minutes of silence here, let me just ask you to pause it, come up with your answer, and then restart the video. Okay, I'm going to give you the answer now, so if you don't have it yet, make sure you paused it and think about it. But here's the answer. Well, I'm not even going to give you the answer. I'm going to start to just talk it through. So the plus charge, remember that the direction of the electric field is the direction of the force on a plus charge. So this plus charge is going to feel a force in that direction. This minus charge, the electric field line is opposite the direction the minus charge would feel a force. So this minus charge feels, whoops, something happened. Not sure what. So this minus charge feels a force in that direction. Are these two forces the same? If they're the same, then the net force is 0, but they're not the same because these field lines are spread out more here than they are here, and so that the force on the minus charge must be bigger than the force on the plus charge. So there is a net force to the left on this dipole. Again, because the field lines spread out more to the right, the field is smaller to the right, so the field exerts a smaller force on a charge to the right. And remember, in a dipole, the charges are the minus charge and the plus charge have the same magnitude. One is just minus and one's plus. So the plus charge, in this case, in part A, is going to feel a smaller force than the minus charge, and so there's going to be a net force to the left. So by that same argument, that even though this one, in B, this one's at an angle, the plus charge is further to right than the left, so the plus charge is going to feel a smaller force. The minus charge is going to feel a bigger force, so there's still going to be a net force to the left. Notice that the other thing about B is that because it's at an angle, it also feels a torque, so it also rotates, but we didn't ask about that. Okay, so now let's look at C. So this is a picture that we haven't seen before, but this is a valid field in C. Notice that the field lines don't get any farther apart on the right than they do on the left. So what does that mean about the field or the force? That means that the field is constant, that the force doesn't get any smaller as we get farther away. And that's perfectly fine. We just haven't seen that situation before. And so that means that the force at the plus charge, the force which points to the right, is equal to the force at the minus charge to the left. Those two forces are equal because the field is equal at the minus charge and at the plus charge. So the net force in this case is equal to 0. Okay, so now probably you can answer for yourself. What about part D, well, in part D, well, maybe not. Maybe it's not obvious. In part D, again, look at the field near the plus charge and the field near the minus charge. The field lines are still separated by the same distance, so the force is actually the same, right? So we got a force there and a force there. Those two forces are the same. So what's the net force? The net force is 0. So the answer is C and D. Both feel a net force. But you might say, but there's something different about C and D, right? In D, just like in B, because those two forces are not along the same line, there is a torque, and the whole thing is going to rotate. Now, we didn't ask about torque, so that's not important here, but there is a torque that will rotate that dipole until it is in the position of C, right, where there's no net torque. Okay, I think that's probably enough for today. In next class, we're going to start talking about not field mapping. We're done with field mapping. We're going to start talking about calculating the fields by multiple charges or continuous charge distributions. And so that's actually the next. That's the rest of the field chapter, and then the next chapter, which is Gauss's law, is all about calculating fields due to continuous charge distributions. How do we get more complicated fields and more complicated charge distributions? Not necessarily complicated, but just not the single point charges. They're really relatively they're relatively easy to do. We just need the tools to do it. So next class we're going to talk about continuous charge distributions and the fields and therefore the forces due to continuous charge distributions. Have a fantastic weekend.